So yeah, let's thank you for the nice introduction. I'm very happy to be here, and I think because my title is a mouthful, I'm starting sort of backwards and already give you the result. But basically what we're trying to show here is that if you have a topological non-trivial spin structure as the one shown here, then what you will experience is that the magnons actually have a magnon Hall effect. And so we do this by looking at the magnons spectroscopically. You may wonder why this is even interesting. So the motivation was actually sort of also given by Christian in his talk. So I will not say very much about magnonics also because this is something that I personally don't care much about. So my motivation is more understanding sort of the fundamental effects and of course having sort of a Hall effect of bosonic quasi-particles is an open question research anyway. So here's an example for a frustrated magnet where basically the team has measured sort of a thermal Hall conductivity and has associated this with the magnons experiencing this magnon Hall effect. There's also some spectroscopic measurements in those systems where basically people focus on measuring sort of topological non-trivial magnon bend structures. And of course, this leads to a Berry curvature that would lead to such a Hall effect as well. So in our case, as I said in the beginning, we follow a different proposal where sort of this is coming from a real space spin texture that is topologically non-trivial. And so with this sort of summary at the beginning, I can quickly introduce my group that is situated at the Pauschere Institute mostly, but also doing part of their work at the University of Zurich. This work, however, is something that has followed me many, many years. So the true collaborators are actually shown here. I would say this is maybe a project that was 10 years in the making. There's a lot of beam time at various facilities that we use to measure those magnons. And so with this, maybe I can jump in with my outlook. What I want to do is give you a bit of history on what Skermions actually are, what the topology is behind them, and why this leads to a certain functionality also. And then I come back to those magnons running in circles. Okay, so let's start a bit with the history. So I spent myself about 8 years at Los Alamos National Lab. This is a slide that I stole from Abad Saxena down here. He's a group leader of a theory group at Los Alamos currently. And what this shows is actually the roster of the theory division in Los Alamos in 45. And so if you look at this, you see many famous names. At least if your field is physics, you should know these. So there's Bethe, Weismann, Neumann, there's also Feynman. And then over here, there's another fellow called Tony Skerm. And he's also shown on this side. So my feeling is that in this good company, he was thinking about a lot of good stuff. And indeed, we see him sitting here in New Mexico on the top of a mesa thinking. And so a little while later, he actually came up with something that is called the Skerm Model. So this is basically a nonlinear field theory shown here that basically treats massless pions. And so those are particles which can be represented by a topological integer. So without going into too much details, we can then think about what such a skyrmion is. So I mean, I already said, basically in such a field theory, we describe particles as wave-like excitations. So this is like a resonance on a string shown here. And this immediately actually shows you an important issue that you have that is a particle stability. So if you basically look at this, of course, this resonance on the string has a higher energy and higher momentum than the ground state, which is basically the string at rest, but it's also characterized by a finite lifetime. So this will decay quickly. So then basically the question is a bit, how do you get stable particles? And so good old Tony Skerm, how he solved this was basically by introducing a topological integer. And that cannot be changed by a continuous transformation of the field configuration. And so now with this in mind, we can think about the stuff that I'm working on, which is sort of magnetic skyrmions, and how they come together and how they're topological. So here I'm basically cheating a bit because I'm just looking at a special case, but I think it's the most hilarious one that you can look at. So how do I actually get such a magnetic skyrmion that is shown here? So basically I can start with a sphere. So this is basically a 2D surface in a way, and I can decorate it with spins. And then what I can do is I can sort of take a comb and I can put them all to the side. And what I get then is basically I get sort of two tufts, one on the North Pole and one on the South Pole. I'm sure if you have tried to get your hair in order in the morning, this is a phenomenon that you're quite familiar with. And then when you project it down on a 2D plane, essentially you will have the South Pole tuft, so those are spins pointing down in the center, and then at the circumference you have the North Pole. So why does topology matter here? We can come back to the good old donut. And so you can see here easily, if you would do the same trick, starting with this donut that has a different topology, you would not have the tuft. So I'm not sure that this means you should have a donut-shaped hat to basically solve your problems in the morning, but it tells us a bit how this topology actually influences the properties of those materials. And so this is something that I will show quickly now, if this goes forward. Okay. Okay, so basically we can then formalize this a bit. And here I'm showing a different skyrmion, so this is not a Bloch skyrmion, so I'm not doing this combing trick, but it comes down to the same thing mathematically. So again, you start sort of with this order parameter manifold, you project it down in a 2D plane, and what you can define then is this beast, which is called a topological skyrmion density. So it's basically sort of a cross product of a unit vector that points along the local magnetization. And with that, you can define a binding number. So once you integrate over the skyrmion here, then you will find out this number is -1 in this case. And you can actually find many of those. So I already mentioned before the block skyrmion that I showed you using my comb trick. Here's the nail one, and then the different other versions like anti-skyrmions. You can have then bi-skyrmions that have a higher topological number and so on. So why is this interesting? Well, basically it comes down to the concept of the Berry phase, which is shown, of course, here. I think most of you are familiar with, but basically what this means is if I have a particle that basically travels on a closed loop here, I basically accumulate an additional geometric phase. So this is shown here with the arrows. We can see if we just follow adiabatically that I get an additional angle here. So if we think back about our skyrmions, basically the same thing that happens here. So if I have, let's say, a particle with a spin traveling along this texture, so I'm going from sort of the circumference to another point on the circumference, that basically corresponds again to this closed loop here. So I will collect this phase, and of course I will also follow the spin texture. So what this will actually lead to is that if I look at it precisely, is that my electron, in this case, if I use a charged particle, will travel with such a curve. So this will lead to an additional Hall effect. So if I do a transport experiment, as shown here is a conventional Hall geometry, I will pick up an additional Hall effect due to the topology. So this is one of the first experiments in such a compound, actually done in Christian's group. And so all other Hall contributions are already subtracted here, but in the phase where we have this non-trivial spin texture, we see this Hall effect. So basically what this boils down to is sort of that the spin texture with the Berry phase acts like an effective magnetic field that can be estimated, and it's very big. So this field is larger than 10 Tesla, so it's a very large effect. So you can then actually go a step further, and you can see that basically in addition to the electrons doing this topological Hall effect via the spin torque, you can actually also move those Skermion textures. So this is the so-called Skermion Hall effect, and this leads also to an additional electromagnetic induction that is emergent, and this also has been shown by transport measurements. I will not go into much details here, but this is essentially where the hype about those Skermion materials come from, is that you can easily move them using such a current. So this is a by now pretty old experiment that was done in argon, but they basically use microscopy, and they basically have a magnetic material with domains that by applying a current, they feed through this geometrical constraint, and they rip this apart into Skermion bubbles, and they can move them, and you can even see the Skermion Hall effect. So this has quickly led to the notion that this would be useful for devices, and now there's many experiments along those lines. People are doing also sort of Skermion gates and Skermion logic and all kinds of things with it. So with this, I basically come back to the magnons, because if you think about the electron sort of as a quasi-particle, in principle, you could do the same thing with a magnetic quasi-particle. And so how would this go about? So in principle, it's the same principle, but I will give you a bit the math behind that was done by my collaborator, Marcus Gast. So in principle, you can write down a Landau-Lifshitz equation, where you basically have the precession of the magnetization with a gyromagnetic ratio around an effective field. And so this effective field is, of course, given by the magnetic texture in this case. So you will basically smoothly vary your magnetization around this texture. So you can use this basically going one step further and put this into a spin wave representation. So here we have a spin wave function. And again, basically what you can express is sort of an elliptical precession around the equilibrium magnetization, sort of shown in this coordinate frame, given with those vectors here that are basically the direction perpendicular to this equilibrium magnetization. So if you then look at this Berry phase that I showed you before, in case you have a locally varying magnetic texture, then you can calculate that basically your magnon will collect such an additional Berry phase. So this then immediately leads to a Berry flux that depends on basically your topological Skermion density. So if you start with this winding number, you can find that every Skermion that you have, every one of those objects, basically contributes with 2 flux quanta in this case. So this is the magnetic field they will experience. And then what this will lead to is basically that if you have magnetic waves impinging on such a magnetic texture, that you will feel sort of an emergent Lorentz force, and your magnetic waves will see such a Hall effect. Okay, so the question is a bit, how do you measure this? And we did this spectroscopically. We do this using a system that's very well characterized called manganese silicide. It's actually a non-central symmetric Haley magnet that basically has 3 energy scales that lead to this order. So on the largest scale, you basically just have ferromagnetic exchange that leads to the moments basically looking all in the same direction. And then because of the broken inversion symmetry, you get an additional interaction called the Cieślinski-Maria interaction that basically wants to cant neighboring spins. So with that, you get a very long wavelength helix. This is basically the ground state. And then you have higher order dm terms that lead to cubic magnetic anisotropy and pin basically the helix along certain directions. So now, if you look at the phase diagram of this material, basically we have temperature here and magnetic field there. The phase diagram is pretty complex because you can, of course, apply a magnetic field that will tilt sort of the helix, the spins in the helix towards the magnetic field. And then for a very long time, there was basically this phase pocket below TC that was called the A phase, and eventually this was realized this is a Skermion lattice. So it's a lattice of those various Skermions. So there's a whole list of publications that study basically the magnons in those various phases. The yellow ones are the ones where I have contributed, and then there are some of my collaborators as well. So why I'm showing you this is basically just to say this is a system that we understand very well. So it's ideally suited to basically look at this Magnon Hall effect. And this is basically what we did in this latest study. So basically, if you use those equations that I've showed you before, and that's what Marcus did, you can essentially calculate the spin wave spectrum inside such a magnetic unit cell that contains one magnetic skyrmion, and you can see sort of the spectrum here. There are basically three modes that are easy to visualize. So they correspond to basically a clockwise rotation of a skyrmion center, then of course the counterclockwise one, and there's also a breathing mode. This was already measured a while ago, so this is also a few years back using basically microwave spectroscopy. But then this only probes those states sort of at zero wave vector. So the idea is how do you get to the rest, and we will do this by neutron scattering. But before I do this, I want to sort of show you a back of the envelope calculation. So basically, like in the normal Hall effect that was by electrons that Johannes just discussed, of course, we will also have sort of cyclotron orbits here in a way. So I show this here for basically electrons, but we will have the same thing for magnons. And you can then ask yourself sort of what is the separation of the different Landau levels that you have here. And so basically what you know is each skyrmion creates a flux of basically two flux quanta. Then to basically get to the magnetic field, you have to look at the flux density. So you divide this by the area of such a skyrmion that you can calculate. And then the cyclotron frequency is given by this effective field divided by the mass of the magnon. So then you can compare this with sort of the characteristic energy scale of such a magnon. So here we just consider basically a free magnon. And then you can plug in the numbers. And basically what you get out is that we expect that the Landau levels are separated by 10 microeVs. So this is a not very large energy scale, and it's, I would say, well beyond the reach of normal neutron scattering. So this is a real challenge, but we still managed to do this. And the way we did it was basically by combining three methods. Two of them are pretty standard, so this is time-of-flight spectroscopy and triple axis spectroscopy, which are done since many years. This technique, for instance, also led to a Nobel Prize several decades back. I think one thing that you should take away is how big those instruments are. So this is basically not the entire instrument. This is just the vacuum vessel that contains the detector bank here at the back. And you see a person standing here for reference. So those are those large-scale machines that we use. Then at the end, the key method that we use is so-called Mises spectroscopy. You will see this has nothing to do with a cat, but it's still very useful. And then I just want to, before I move on, say a few words about length scale. So we saw a talk this morning by Christian Bach, and he also was looking at spin waves, but he basically probes them sort of at very low wave vectors. Whereas what we are trying to look at is sort of on the other end, basically at wave vectors that are much longer than the helical wave vector. So sort of this ties together those two methods. So here's a bit more of the theory. So instead of just showing the modes that I showed you before in the first Brion zone, this is an extended scheme where we basically show at the band structure going outside of the first Brion zone. And again, we can identify those various modes. And then we can ask ourselves, what would the neutron scattering probe? So if I basically show you just this box, which is positive energies, and then a standard time-of-flight experiment, which is still very hard to do on those materials, then you see that basically this green box would correspond to this box in the theory if we basically extend this Magnum spectrum to even larger wave vectors. So we indeed did this. So this is the experiment that you see here. And what you will tell me is, okay, I can't tell much in this area. I see that there's some intensity, and it's probably right, but I can't look at those different modes. And this is, of course, because the spacing of them is so small. So we basically went one step further. So this is the experiment that I already showed you. So we used the polarized triple axis spectroscopy to do finer scans along the spectrum. And so this is now basically the same pattern as here. It's just tilted by 90 degrees. It's easier to compare with the scans. And so we basically did a few scans along those spectra. The different colors are basically different initial polarization. So there's some polarization dependence also, which for the moment is not so important. And again, I mean, basically what we can do is we fold the spectra with the instrumental resolution. If we do that, basically the dots that you see that are the experiments, they're well explained by the theory, but again, we cannot differentiate those single Landau levels. So for that, we had to go to this instrument, which is in the reactor at Munich. It's quite unique. Basically, I would say this is the only such instrument worldwide that actually produces result. There's another one in Japan that is sort of in development, I would say. But let me quickly explain to you how this works. MEETS actually stands for modulation of intensity with zero effort. And so what you do is basically you come in with your neutron beam, and it runs through a polarizer, which means that all the spins of the neutrons in the beam are looking in one direction. And then after you have a set of complex flippers, but basically what this does is just that you process those neutron spins in a plane. And then what is quite unconventional is that you put an analyzer actually in front of the sample here. So what you get at the sample is actually an intensely modulated pattern, which is where the name comes from. So if you now just look at elastic scattering, essentially nothing happens, and in my detector I get exactly the same pattern. What we, of course, want to do is we look at inelastic scattering from our Magnum spectra. And so what happens then is basically that some of the neutrons will basically get slower. This is the blue arrow, and some will get faster. So what happens then is that the contrast of this modulation gets squished. So I can do this for many settings. So doing different settings basically corresponds to different times. And with this, I get a very high resolution because essentially my neutron precesses very often in this field. So I have very high precession in this precession degree of freedom. So the result, what I get is basically a Fourier transform of my scattering function. This is basically shown here. So we can Fourier transform it so that we are, again, in energy space, which is what we like to look at. And this would then be the result. And so here we, you already have questions maybe. And so essentially what we get here is indeed that we can resolve those different modes. So this scan here is then basically this bar shown over here. There's a bit of a difficulty that in the way this experiment was set up that we cannot uniquely look at the Skermion lattice phase. We also see some contributions from the surrounding sort of helical phases. So we have to take into account those modes as well, but they can be calculated. But we can put everything together and essentially resolve all those modes with this spacing. So indeed, we can resolve those Landau levels. And I think that the result is that we basically see that this effective field that emerges from the Skermion texture makes those magnons propagate in circles. So this is, of course, something that, in a way, you would like to image and maybe also measure the thermal Hall contribution from it eventually. But all our results are consistent sort of with this assumption. So, and with that, I thank you very much for your attention, and I'm happy to answer your questions.
Okay, thanks very much. Are there questions? Oh, speak there.
Yeah, very nice. One question. So you have all these magnon bands, you know, tightly spaced together and so on. So what about magnon-magnon interactions? I mean, in principle, they could smear the signal even further, but you don't seem to see any signatures of that.
So you're talking about the inherent broadening of the magnons.
Yeah.
Yeah. So I mean, this is something that we already observed even in the helical phase. That surprisingly, those magnon states are very sharp. So I don't understand fully the reason for that. But I think it's maybe somewhat a lucky coincidence that we can resolve it in that way. Yes. Yeah.
Okay, because in this whole non-collinear structure, you would actually expect that you get very strong broadening. Okay.
Yeah.
Good.
Are there further questions or comments? Okay, so perhaps I still have one question. There's one thing that you didn't, I think, specifically address are the Chern numbers of the magnon modes. Do you want to comment on those, perhaps?
Yeah, so I mean...
Since the title was Topological Magnons.
Yeah, that's true. So, and there's, of course, a reason why I lightly skipped over this, because then there's another question that I think we currently can't answer. So, I mean, so basically, if you look at this column here, you see that we have calculated the Chern numbers for those magnons, and some of them are not zero, so basically they're topological non-trivial. So then the question that I would expect from you is essentially, so where are the surface modes? And with what I do, I can't measure those. So this is very much something for the future to figure out how to do this. But it's right that, I mean, to get this Magnon Hall effect, you need those bands with non-zero Chern numbers. Yeah. Yeah.
Okay. If there are no further questions or comments, then I think we would like to thank you, Marc, again for this presentation, and we'll move on.